Math 2b practice set 11, graph the function 6x plus 2y equals 12. This function can be transformed into slope-intercept form, which looks like this: y equals m times x plus b. This equation has two variables, x and y, and it has two parameters, m and b. These parameters are: m is the slope, which is the rise over the run pattern, and the other parameter is the y-intercept b. So those two values together, the rise run pattern and the y-intercept, will define any line that you can think of on the Cartesian coordinate plane, with one exception. That is a slope with potentially no y-intercept and a slope with a line with undefined slope. So those are vertical lines. But other than that, that one exception, this works. So what I'm going to do is I'm going to transform this equation by isolating the variable b. So from each side of this equation, I'm going to subtract 6x, and then I'll rewrite it. So this equation is now 2 times y equals negative 6x, and then plus 12. And then I'm going to divide both sides by y. So y is equal to negative 6x over 2 plus 12 over 2. And if I simplify that further, I say that y is negative 3x plus 6. So my parameters are, my slope is negative 3, and I can interpret that as down 3 and to the right 1. And my y-intercept is at 6. So to graph that function, I'm going to go ahead and begin at my y-intercept of 6, and I'll place a single dot at that point. And then from there, I'm just going to follow my slope pattern of down 3 units, 1, 2, 3 units and over 1, down 3 units over 1, down 3 units over 1. So at a certain point, it's pretty clear what's going on. This is equivalent to the going up 3 units and back 1 unit as well. So both of those are equivalent slopes. And once I have enough points that I have a pretty clear idea of what's going on, I can grab the straight edge and go ahead and draw the line that goes through those points. So that's the graph of y equals negative 3x plus 6. Number 2 asks us to graph the function y equals x squared plus 4x minus 5. We've practiced factoring enough, and that's a great way to figure out what the roots of this equation are. So for example, when y is 0, that's when this particular function would be crossing the x-axis. So if we have real roots, by setting y equal to 0, we're likely to find them. So I'm going to go ahead and write the equation. 0 is equal to, and then I'm going to write this quadratic in factored form. So it's x minus 1 times x plus 5. And again, you can use any technique that you'd like to factor that. Once I have it in the factored form, if I set each individual factor equal to 0, I can see that I have two roots. One of them happens to be at positive 1, and the other root happens to be at negative 5. So a good place to start with your graph of the function is to graph those roots. So I'm going to come over and I'm going to graph one root at negative 5, and I have the other root over at positive 1. The next thing that I like to do, and it's I think fairly straightforward for this function, is I'm going to add to this the y-intercept. So if x was equal to 0, right? If x equals 0, that's where we cross the y-axis. That's when we find our y-intercept. And if x was equal to 0, this term is 0, this term is 0. So I'm left with just negative 5. So when x is equal to 0, I'm crossing the y-axis at the point negative 5. So I have this point that is also part of the function. So I'm inclined to think that it is opening upwards, and I know that because of the positive x squared coefficient. Let's see if we can find the vertex. We have been rewriting these in vertex form to find the vertex, and I'm going to go ahead and do that. Our technique has been completing the square. So if I consider the function y equals x squared plus 4x plus some value to make a perfect square trinomial, and then I still have the negative 5, and then I'm going to subtract right here whatever I end up adding to make a perfect square. So to make a perfect square trinomial, because my leading coefficient a is 1, it's just going to be half of b squared, so it's 4. So I'm going to add a 4 here, and then I'm going to subtract a 4 at this point to make it stay equal, to not change or modify the function. So my first three terms will factor as a perfect square trinomial. This is y is equal to, in parentheses, x plus 2 quantity squared. If I multiply x plus 2 times itself, I do get x squared plus 4x plus 4. And then I have minus the number 9. So there's my function, y equals x plus 2 quantity squared minus 9. And from this, I can see my vertex. I remember vertex form, it's y equals x plus, x minus h squared, and then plus k. So the upshot is that the vertex is at the point h comma k. So when I look at this, I can see immediately that my k value is the number negative 9, and h actually has to be the number negative 2, because this negative symbol lives in vertex form right there. It's x minus h. So I am going to take the opposite of negative. Well, let's put it this way. If h is equal to negative 2, then I have the opposite of negative 2, and that's why this becomes a positive. So h is the value negative 2. Another way to think of it is h is the value that will make this thing that's being squared equal 0. So my vertex is at the point negative 2 comma negative 9, and I'm going to add that to my graph as well. So right here at negative 2, we're going to go all the way down to the number negative 9. So at this point, we've got our vertex, which also gives us what our axis of symmetry is. This parabola is completely symmetrical about this particular line. That lets me add this dot right here, this point. The point is negative 4, negative 5. That's true because the symmetry going to the y-intercept. So with just those few points, I'm ready to graph this. If I wanted an additional point, I could pick another value and get it, but I think I'm happy to just kind of sketch the graph at this point. And it's kind of important. It's not an absolute value function. These should not be straight lines. They're definitely a curve. So find the product of the binomials 3x plus 2 and 4x minus 1. Across the top, I'm going to write 3x and then a positive 2. And then down the left-hand side, I'll write a 4x and a negative 1. So I need to find the area of each of these individual squares. This first one is 12x squared. 3x times 4x is 12x squared. The one immediately below that would be negative 3x. Over here to the right of that, I should have a negative 2. And then my last box would be a positive 8x. So when I combine these pieces, I get that the product would be 12x squared. And you can see I'm combining a negative 3x and a positive 8x. So that would be plus 5x and then minus 2. So this is the product of these binomials. Simplify the given quadratic expression. To do that, I'm going to go ahead and multiply out the binomial. It's a binomial squared, and then I'll combine like terms with it. So when I multiply x plus 1 squared, I get x plus 1. Well, actually, no, I don't get that. I was going to write it out, but you know what? I can just write this. This is x squared plus 2x plus 1. And if you're not getting that when you square the binomial, I recommend that you write out x plus 1 times x plus 1, and then perhaps consider what happens in a similar fashion to question number 3. So I've got this, and then I'm going to add to that 2x, and then I'm going to subtract the number 5. So if I simplify this, I can see I only have one quadratic term. I've got the x squared, and then I'm going to add to that 4x, and then I've got a positive 1 and a negative 5, which is negative 4. So this is the simplified version. There's actually less operations necessary to evaluate this particular expression. Factor the quadratic trinomial 15x squared plus 11x plus 2. Again, to factor means that we're taking something that's the sum of terms and we're attempting to turn it into products. I'm not asking you to factor quadratic polynomials that can't be factored at this point. We have talked about the discriminant, and we do realize that there are tests to see if something can be factored, but if I'm asking you to factor, it will be factorable. So if in the AC method of factoring, I've got 2 times 15x squared, so this is 30x squared, and then down below I have an 11x. So I'm looking for two terms that have a product of 30x squared, and they have a sum of 11x. And 6 times 5 is 30, and 6 plus 5 is 11. So my terms are 6 times x and 5x. So if I consider my factor puzzle now, I've got down here the 15x squared. Up here is the number 2. I've got a positive 6x and a 5x. The factor that I can pull out across the bottom here is each of these have a common factor of 5x. The factor that I can pull out going straight up is each of those can be divided by 3x. And 3x times a 2 would give me 6x, and 2 times 1 is 2. So if I look at these and double check, yeah, 2 times 3x is 6x, 2 times 1 is 2, 5x times 1 is 5x, and 3x times 15x is 15x squared. So combining my two like terms, the factored form then is 5x plus 2 times 3x plus 1. So this is my answer. This is this quadratic trinomial in its factored form. Number 6 says solve for x. You're given a quadratic trinomial 3x squared minus 13x minus 10. 3, 13, and 10 don't have common factors, so I'm not going to be able to factor out a greatest common factor first. In the AC method, 3x times negative 10 would be, in this case, a negative 30x. And then down below I have a negative 13x. So I need two values that have a product of negative 30 and a sum of negative 13. Sometimes when I'm stuck, I do like to write out kind of the prime factorization, if you will, of 30. 30 is 3 times, well, it's 2 times 15, and 15 is 3 times 5. So 1 times 2 times 3 times 5. So these are the factors that I have to play with, and I have to divide them up into two groups because I know when I multiply those, I do get 30, and when I add them, I have to get negative 13. The other thing is obviously because I have a negative product, one of these will have to be a negative number, and the other will have to be positive. And because I see that my sum is negative 13x, I know that the negative one must be larger in magnitude than the positive value. So it doesn't take a lot of time looking at this, and I can see, well, I've got, let's consider negative 15x and a positive 2x. So when I do multiply those, I have negative 30x. This was supposed to be squared. And when I add them up, I do get negative 13x. So my strategy here to solve for x is to factor this and then use a zero product property to set each factor to 0 to find out what x is. So now that I've got this part of my factoring process done, I'm going to go ahead and write the 3x squared minus 10. So here's 3x squared, and here's the negative 10, and I'll write a negative 15x here and a positive 2x here. So going along the bottom, there's a greatest common factor of just not 2. those can both be divided by x. And going straight up, I have a common factor of 3x. Now, 3x times a negative 5 would produce negative 15x. And then finally, negative 5 times a positive 2 would produce negative 10. And at this point, again, I pause to just double check. 2 times x is the 2x. 2 times negative 5 is negative 10. 3x times negative 5 is negative 15x. And 3x times x is 3x squared. So this is the factored form. And the factored form is 3x plus 2 times an x minus 5. So now that I have the factored form of this quadratic, I'm going to go ahead and set each, let me write it up here, 3x plus 2, and then there's an x minus 5. So now that I have this, the only way that I can get a product of 0 when multiplying two values is if one of the values is 0. So the zero product property says in order to figure out values of x that would work, set each one of these equal to 0. So I'm going to write 3 times x plus 2 is equal to 0, and I'll also write x minus 5 equals 0. In the first case, this means that 3x has to equal negative 2, therefore x is negative 2/3. This is a value of x that would make that works in the equation up above, right? That works. And the other value that works is x is equal to positive 5. Number 7 is a pretty straightforward linear equation. It asks us to solve for x. There's lots of ways that you could approach this. For example, you could start by using the distributive property to eliminate the parentheses on the left-hand side. If I did that, this would become 6 times x. Again, what am I doing here is I'm multiplying the 3 times the 2x, and I also need to multiply the 3 times 4, so plus a 12 plus 7 equals 2x minus 10. If I simplify the left-hand side further, I have 7x. Let's see, 12 and 7 is 19, and that equals 2x minus 10. The next thing I could do perhaps is I could subtract 2x from both sides. If I take away 2x from each side, I do eliminate the x's on the right-hand side. The left-hand side ends up having 4 x's because I have 6 of them, take away 2. Plus the number 19 equals negative 10. Next, I'll take away a 19 from each side. That leaves me with 4x on the left-hand side and a negative 29 over on the right-hand side. And then finally, in order to solve for x, I'm just going to divide both sides by 4. So x equals negative 29 fourths. I encourage you to grab this value, 29 fourths, and look at it on your calculator. Perhaps as a decimal, this is negative 7.25. Remember, this is a solution if and only if, when I plug it in for both values of x's, this value of x and this value of x, it has to be the case that everything on the left-hand side ends up equaling exactly what's on the right-hand side. So when you plug negative 7.25 into the left-hand side and the right-hand side, you should get the exact same value if this value, negative 29 fourths, is indeed a solution. Question number 8 says, find the length of CA. Round your answer to the nearest tenth. So CA is this side here. This is what I'm looking for, and I guess for convenience, I'll just call this x. This is what I'm looking for. So if I'm trying to find the length of CA, and I have, for example, this angle is 35 degrees, and I'm also given that the opposite leg is 10, I can see that I could use the tangent ratio to figure out what x is. In fact, the equation that I could write is the tangent of 35 degrees is equal to the opposite leg, 10, divided by the adjacent leg, x. And again, I always encourage you, if you end up getting your variable in the denominator, it's a good idea to multiply both sides by that value to get it out of the denominator. So this equation becomes x times the tangent of 35, and that equals just plain old 10. Now, to solve for x, I'm just going to divide both sides by the tangent of 35. X equals 10 divided by the tangent of 35. Make sure your calculator is always in degree mode before you set out to evaluate an expression like this. If you are set in degrees, that's mode. If you hit the mode button, you can check. You should get that x is equal to 14.3 units when you round to the nearest tenth. So in this picture, it looks like it's roughly drawn to scale, right? If this, no, it's not. It's a little short. But if indeed this was 10 units, and this was a 35-degree angle, it would have to be the case that this would be 13 or 14.3 units long. Number 9 says solve by completing the square. Interesting thing, this is actually the same exact problem as number 2. In number 2 we solved it by factoring, so either technique would work for this, but this one I'd like for you to do with completing the square. As we know, sometimes quadratics are not factorable, but we can always get at their roots, real or imaginary, by using the method of completing the square. So if I look at the left-hand side, in order to make the left-hand side a perfect square trinomial, what I would need to add is 1/2 of the b value squared. So 1/2 of 4 is 2, and 2 squared is 4. So I'm going to add a 4 to that side. And when I do so, I need to add a 4 to the right-hand side also to keep the equation true, right? I'm claiming these are equal, so I just added 4 to each side. They're still equivalent to each other. Over on the left-hand side now, I have a perfect square trinomial, and this factors as x plus 2 quantity squared. If you doubt me, I encourage you to multiply x plus 2 times x plus 2, and you'll see that it is indeed x squared plus 4x plus 4. And over on the other side, we have the number 9. So the next step, now that I have a perfect square trinomial on the left-hand side, is to take the square root of both sides. When I do that, I get over here an x plus 2, and that equals plus or minus the square root of 9. Now I'm going to suspend simplifying that for just a minute because I want you to see my answer. The answer is x equals, and it doesn't really matter where you place it. Normally I like to place this value in the front, so I've got a -2 plus or minus the square root of 9. Now, if it turns out that you have a square root of a perfect square, you should evaluate this and get both values. However, if 9 was not a perfect square, this is probably the preferred answer. I'd like you to leave it exactly like this. However, in this case, because 9 is a perfect square, I want you to realize that we have two answers here. One of them is -2 plus a 3, and the other one is a -2 minus a 3. So you see what I've done. I've just broken this up into two cases, one for the positive and one for the negative. -2 plus 3 is equal to 1, and -2 minus 2 is -5. So you can see my values are x is 1 or x is -5. So my values are 1 and -5, and those are the exact same answers that we got in question number 2. Number 10, solve by completing the square. X squared minus 6x equals -5x. So what I'm going to do is complete the square on the left-hand side. And as I do that, I'm going to be adding a value that I need to also add on the right-hand side to maintain the equality statement here. So on the left-hand side, I've got x squared minus 6 times x plus, what I need to add is half of -6 squared. Well, half of -6 is -3, and -3 times -3, or -3 squared, is +9. So I'm adding a 9 to both sides. Over on this side, I've got a -5 and then plus a 9 also. So on the left-hand side, that is now a perfect square trinomial. This factors as x minus a 3 quantity squared. Again, if you multiply that out, you would get x squared and then a minus 3x minus 3x, which is exactly the negative 6x. And then when you multiply negative 3 times negative 3, rather, you would get a positive 9. Over on the right-hand side, we end up with just plain old 4. So I have a perfect square equals some value. So I'm going to take the square root of both sides. So that means that x minus 3 equals plus or minus the square root of 4. And I think it's unfortunate that both of these had perfect squares that we were taking the square root of. This is usually not the case. If you do get a perfect square there, you can factor this. But anyways, I'm going to leave that for just a moment, and I need to add a 3 to both sides to get what x is. So x is equal to 3, a positive 3, plus or minus the square root of 4. Again, if this was not a perfect square, this is where I would like for you to leave your answer. There's two values there, 3 plus root 4 and 3 minus root 4. However, if it is a perfect square, I'd like you to write those out. So the values of x that work are 3 plus the square root of 4, which is 2. And the other one is 3 minus the square root of 4, which is 1. So my answers are 5 and positive 1 in this case. So those are my answers. X could be 5 or x could be positive 1.